Shri Gurubhyo Namaha, children. We welcome you for our online teaching academy, Ekalaiva. Today we are going to continue with 12th standard state board physics, chapter number 4, electromagnetic induction and alternating current. We are going to discuss resonance in series, RLC circuit and Q factor. Let us move on to resonance in series. Resonance in series RLC circuit. Okay, so this is an RLC circuit, a resistor, an inductor, and a capacitor. Now all these three are connected to an alternating source. Okay, so AC. Now the resistance of this resistor is R. The inductance of the inductor is L, and the capacitance of the capacitor is C. So all these three are connected in series. There will be a current flowing in the circuit. Now resonance occurs. Now when resonance occurs in a series RLC circuit, now resonance occurs when the frequency of the applied alternating source, that is represented as omega r. So omega r represents the frequency of the applied alternating source, which is the voltage that is applied here. Okay, the frequency which is applied here. Now when this is equal to the natural frequency of the RLC circuit. So natural frequency formula is given as 1 by root of LC. This I will tell you how this value came. Okay. So when the frequency of the applied alternating source is equal to the natural frequency of the RLC circuit. Now in this condition, that is, now here let us consider the value of resistance. Resistance value is represented as R. And here also you have resistance which is represented as XL, which is called as inductive reactance. Now here you have capacitive reactance which is represented as XC. So in a resonance condition, resonance occurs when the value of inductive reactance is equal to the capacitive reactance. So this is the resonance condition when XL is equal to XC. Okay, so in that case, what will happen? The current in the circuit, okay, the current in the circuit reaches maximum value. So this is the resonance condition, or this is called as electrical resonance. At electrical resonance, the inductive reactance is equal to the capacitive reactance. So let me tell you how this formula came. 1 by root of LC. Now we all know that the value of inductive reactance XL is represented as omega into L. Now since we talk about angular frequency at resonance, let me represent this as omega r. So omega r L is equal to, now here we know capacitive reactance is given by the formula 1 by omega C, and again here I will write omega r. Okay, now bring this omega r to the left side. Already we have one omega r, so this becomes omega r square is equal to 1 by LC. Okay, So what will be omega r now? Omega r is equal to 1 by root of LC. Okay, so this is the condition for resonance. Look at the value here. Now what is omega r? Omega r is nothing but the frequency of the applied alternating voltage when it is equal to the natural frequency. Now when this happens, in the condition XL is equal to XC, that is inductive reactance is equal to capacitive reactance. Now in this condition, resonance takes place and the current in the circuit reaches maximum value. Okay, and when the current is reaching maximum value, that is when Im is I suffix m, which means current is maximum. So when current is maximum and when XL is equal to XC, we can say that the circuit is said to be purely resistive. Okay, now here we have discussed so many cases. Okay, like in the previous videos where we discussed about AC with an inductor, AC with a capacitor, AC with a resistor. Now the circuit is said to be purely resistive when XL is equal to XC. We have already discussed the special cases. Now, previous videos we have discussed in RLC circuit, we have discussed the special cases. So, what are the three special cases we have discussed, children? The first case is when XL is greater than XC. When XL greater than XC. Now, in this case, now here, which means the inductive reactance is greater than the capacitive reactance. Now here the circuit is said to be purely inductive. Okay, ma? Then the second case is when XL is lesser than XC, which means the capacitive reactance is more. Okay, so in this case, the circuit becomes purely purely capacitive circuit. Okay, whereas in the third case, we discussed XL is equal to XC. So this is the condition at which resonance occur. Now if XL is going to be XC, then definitely the circuit is said to be purely resistive. So these three cases we have already discussed in the previous video, which is RLC circuit. So this is the condition. In this condition, the current in the circuit will be maximum and the circuit is said to be purely resistive and the circuit is having resonance, or the circuit is said to be in electrical resonance. Okay, so now let us define what is resonant frequency. So resonant frequency is frequency at which resonance takes place. Frequency at which resonance takes place is called as resonant frequency. Resonant frequency. So I'm going to obtain the condition now. We know the formula. We have already written the formula for resonant angular frequency. So resonant angular frequency is represented as omega r. Now this is equal to 1 by root of LC. That is the definition. Frequency of the applied voltage is equal to the natural frequency. So I have written this equation. Now here I can also write, instead of angular frequency, I can simply write this as resonant frequency also. So when I write resonance frequency, now I have the formula which is FR equal to 1 by 2 pi root of LC. Now how this equation came? Now we know that omega r is equal to 1 by root of LC. You know the formula for omega. Omega is 2 pi f, correct? So it is 2 pi omega r, and here also you have fr. So 2 pi fr equal to 1 by root of LC. So fr will be 1 by 2 pi root of LC. This is also an equation for resonant frequency. But here we are going to consider this equation 1. Okay, now I'm going to square this equation. So when I square this equation, squaring equation 1. So when I square equation 1, I have omega r square equal to, now right side I will have simply 1 by LC. Okay, now I'm going to interchange this omega r between this denominator. So here I'm going to split this as omega r into, bring this L to the left hand side, and 1 omega r will go to the denominator. So this will become omega r into C. Now which implies that this is nothing but omega L equal to 1 by omega r into C, which is XL equal to XC. So this is the condition for resonance. So when XL is equal to XC, then you will have the resonance, electrical resonance to occur in a circuit. So when electrical resonance is occurring in a circuit, as I told you, the current value will be maximum. So in that case, value of current will be Im is equal to Vm by root of R square plus XL minus XC the whole square. Now this formula we have already derived in the RLC circuit. Now here at resonance, XL is equal to XC. So when XL is equal to XC, this term will not be there at resonance condition. Okay, so at resonance condition, when XL is equal to XC, what will be the value of Im, children? Im is equal to Vm by root of R square, or I can also write this equation as Im is equal to Vm by R. So this is the maximum value of current, which is given as Vm by R, and the circuit is said to be purely resistive. Okay, the circuit is said to be purely resistive in the condition XL equal to XC. Okay, ma? So the maximum current, now here is the graphical representation. Now here when I take frequency along the x-axis and current along the y-axis. So when I can, as I told you, now the frequency of the applied voltage can be changed, and it can be adjusted in such a way till it reaches the frequency of LC. So here I keep on changing the frequency from 0 to keep on increasing the value. Now when I keep on increasing the value, the current value also will keep on increasing, and at a particular point, okay, current is maximum now, which is represented by a sharp curve. So this, at this point, the value of current is maximum. Now for a small value of resistance, now smaller the value of resistance, sharper will be the peaks. Okay, now look at this. Now here also you have a blue line. Again, there is a variation. Now again, when you keep on changing the frequency for larger value of resistors, the current value also will be maximum, but the curve will be, we'll compare this. Now here the curve is very sharp for small value of resistance. Now for larger value of resistance, the curve is not that much sharp. Look at the difference. Okay, so this is limited by the resistance of the circuit. For smaller resistance, you have larger value of current with sharper curve. For larger resistance, you have a current value to be the curve being not that much sharper as it is for smaller resistors. So this is about series resonance. Okay, now with this we are moving on to the next topic, which is called as quality factor. Quality factor, otherwise Q factor. So what does this Q factor determines? Okay, now this Q factor determines the magnification of voltages, the magnification of voltages at series resonance. So when the circuit is in electrical resonance, now this Q factor determines the magnification of voltages. So how far the value of voltages has been increased, that is determined by Q factor. So once again we consider this RLC circuit, again a resistor, an inductor and a capacitor. Now all these three are connected to an alternating source. You apply a voltage, okay, and you have the condition XL becoming XL equal to XC. In this condition resonance occurs. So in that case what will be the value of current? We said current value is maximum. So I maximum, that is current is maximum. Okay, so if the current is going to be maximum, the voltages across the inductor and the capacitor is also increased. So voltages across L, which is inductor and capacitor, is also increased. Okay, so when they become same, then at a particular frequency called resonance frequency, the circuit will become a purely resistive circuit. The circuit is purely resistive. Okay, so what will be the magnification of voltages at this situation? That is measured as Q factor. So let us define the definition for Q factor. Q factor is nothing but, Q factor is defined as the ratio of voltage across L or C. Either I can take the voltage across the inductive circuit or inductor or in the capacitor. So the ratio of voltage across L or C to the applied voltage. So let me write the formula. Q factor equal to voltage across L or C by the applied voltage. Okay, and we know that if the current is going to be maximum in a circuit, that is when XL is equal to XC, if current is maximum, naturally voltage will also be maximum. Yes or no? So let me write the voltage across L or C. So voltage across, that is maximum voltage across L, let me write. So maximum voltage is Vm. Now when it is across L, I can write it as, according to Ohm's law, V is equal to I into R. So here also I have maximum current, and the resistance is represented as inductive reactance, which is XL, right? And similarly, what will be the applied voltage? Now either I can write XL here or I can also write as XC. Okay, because it is the voltage across either an inductive circuit, inductor or a capacitor. So I have taken inductor, so the value of the voltage is Im into XL. And what will be the value of the applied voltage? Again here applied voltage is represented as Vm, which is also equal to Im into R. So substitute in this formula. Now here I have Q factor equal to Im XL by Im into R. Now here Im gets cancelled. So here is the formula for Q factor, which is given as XL by R. So this is one formula. Okay, now here the applied voltage is also equal to the voltage across this resistor, correct? Because now here this is equal to, that is XL is equal to XC. Okay, now here you have maximum voltages. Now here we can say the circuit is purely resistive. So in that case, the applied voltage is equal to the voltage across this R. So I can here either write as applied voltage or voltage across R. Both are correct. So I have substituted the value of voltage across L or C as IMXL, and the applied voltage is, now when at resonance condition, this also will be maximum, correct? Because this is equal to, this is the same. So the applied voltage is equal to the voltage across VR, so which is given as IM into R. Okay, is it clear, children? So I substitute this. So this will be XL by R. Okay, so this is one formula. Okay, now I can write this value of XL. So what is XL? XL is nothing but omega R into L, right? So substitute XL as omega R into L by R. And also I know the value of omega R. What is omega R? Omega R is nothing but 1 by root of LC. So substitute here. So here Q factor becomes, now I'm going to substitute omega R as 1 by root of LC into L by R. Okay, so this equation will be L by root of LC into R. Now this L can be written as root L into root L. So one root L and one root L gets cancelled. So the formula now becomes 1 by R into root of L by C. Okay, so this is the formula for Q factor, which determines the magnification of voltages at series resonance. Okay, now I can also write this Q factor formula when I consider it to be the ratio of the voltage across the inductor to the voltage across the resistor. Either I can consider voltage across L or C. So if I consider voltage across L, I can write this as VL, and the applied voltage is equal to the voltage across R. So let me write it as VR here. Now this is also equal to this, as I already told you. Now what will be the value of VL? VL will be Q factor times VR. Look at the last sentence in your textbook. Now this is the explanation for that sentence. They say that Q factor indicates the number of times the voltage across L or C is greater than the applied voltage. Now look at this value. Now here VL will be definitely greater than VR. Suppose let us take Q factor value to be 5, approximation. It's not the actual value. Let us approximate it. Let us take some value. Suppose if Q factor is going to be 5, so 5 times VR. So look at the explanation. The Q factor indicates the number of times the voltage. Now this voltage will be either voltage across L or voltage across C. So the number of times it is greater than the applied voltage. So definitely when compared to this combination, this value will be greater than this. So Q factor determines the magnification of voltages at series resonance. Hope the concept is clear for you, children. See you in the next video. To subscribe for our online lessons, please press the subscribe button and you will be receiving our latest updates. Thank you, children.